Hello everyone, this is Aditya, and today we are going to cover Fourier series in a one shot. And in this, I'm going to cover every concept which is related to Fourier series. But before that, please do like, subscribe my channel. And now let's start with the lecture. So first of all, let's start with a definition of Fourier series, and let's see what is it. Okay, so it is a series expansion of a function. Well, this function is a periodic function in terms of trick function like sine mx and cos nx, suppose, okay, is called Fourier series. So basically the expansion of function in terms of trick functions sine mx and cos mx is called a Fourier series. Okay, so it is fine, but let's see that how it comes and what is the idea behind the Fourier series. Okay. So before that, you should know what is meant by orthogonality. Well, let's see orthogonality of a function. Okay, so orthogonality of a function. So suppose not of a function because there can be many functions, right? So suppose you have f1 as one function, f2 as second function till suppose fn, right? And suppose they are defined in the interval x belongs to closed a to b, right? Okay, so now let's see what is meant by orthogonality. So for being orthogonal, two functions must satisfy this x dx. It should be equal to 0 for all I not equal to j, right? If the function satisfy this condition when I is not equal to j, then it is called that these functions are orthogonal, right? Okay, so I hope you understood what is it. For example, well, we will see right now an example, but for now you can assume it like this. Suppose if I substitute I as 1 and j as 2, right? So a to b f1 of x into f2 of x dx, it should be equal to 0 so that they are orthogonal, right? And suppose if I put I is equal to j, in that case it is suppose is equal to 1. So in this case it need not to be 0, right? It is only for I not belonging to, I mean I not equal to 0, right? Okay, so now let's see a set which will use the property of orthogonality of functions, and from that set we are going to come to the conclusion of Fourier series, that why is it important. Okay, so let's see. Okay, so suppose I define a set like this: 1 cos x. Suppose let me define it more properly. Suppose cos pi x by L, then cos 2 pi x by L, and so on till infinity. Then you have another set, I mean another element, another set of elements in the same set like this: sine pi x by L, this is x, sine 2 pi x by L, and so on till infinity. So basically it is of the form, you can say like this: cos n pi x by L, and here n can take values from 1 to infinity, like any value where n belongs to natural numbers, okay, as per the given condition. And similar is the case over here. It will be sine n pi x by L, where m, you can take n or m, whatever variable, m belongs to n. Okay, so clear. Okay, so let me erase this, it is of no use right now. So we have to check whether it is orthogonal or not. Let's see. So first of all, let's see the orthogonality with 1 and cos function. So, and of course here x is from minus pi to pi. Okay. So integral minus, or you can take from minus L to L, right? Okay. This L, okay. Minus L to L of the quantity 1 times cos pi x by L, right? And if you will evaluate it, it will be equal to 0. Suppose n pi x, let me write it clearly, cos n pi x by L, right? And if you evaluate it, you will get it as 0, right? It is very simple integral which you can evaluate. Okay, I don't think so that I need to tell that. Okay, it will be sin n pi x by L divided by n pi by L. You substitute the limit and you will get 0. Okay, just remember this property that sin of n pi is equal to 0 for all n belonging to natural number or integers. But since here we are dealing with natural number, so that is why I am saying over here natural number, but it is valid for all integers even. Okay, so it is orthogonal over here. Minus L to L, 1 into sine n pi x by L. Now the similar case with the sine function in the same set, it is also equal to 0. Okay, understood? It will be equal to 0. Why? Because if you integrate it, you get negative of cos n pi x by L divided by n pi by L. Well, n pi by L is a constant, so we don't need to worry about it. So we have cos of n pi x by L, and the limit goes from negative L to L, right? Is it fine? So if you substitute the limits, you will see that it is equal to 0. I don't need to tell this because it is very simple. Okay. Now next we have negative L to L of the quantity cos n pi x by L into cos n m pi x by L dx. If you evaluate it, when n is equal to m, this is equal to, this is L when n is equal to m, and 0 when n is not equal to m. Well, we are now checking the orthogonality with respect to the cos functions, right? So we can see that if n is not equal to m, then in that case it is 0, which means that this is also orthogonal, right? Correct? Okay. Now let's check with sine n pi x by L into sine n m pi x by L dx. The similar case will happen over here. L when n is equal to m and 0 when n is not equal to m, right? Okay, so far so good, but still one case is left. We have checked with respect to one and the cos function, one and the sine function, the cos functions itself and sine function itself, but still we have to check for cos and sine together. Let's see that also. So integral negative L to L of the quantity cos n pi x by L into sine n pi, suppose m pi x by L, right? M pi x by L dx. So it will be 0 for all m comma n, right? So it tells that the functions orthogonal with respect to the cos and sine functions also. It tells that this set has functions which are orthogonal with each other, right? So I hope that it is clear now, and let me check if I made any mistake, and it is fine. Yeah, data is correct. Yeah. And of course you can evaluate these integrals. You have done this in your 12th grade and in 12th grade, not in 11th. So I hope that it is clear. It is simple. It is sine A into sine B. You have to just break it. You know it. Okay. And the same condition will apply over here also. Okay. So you can try it if you want, but still it is not needed if you only working upon the data. Okay. But still, for your curiosity, you can check the data. That is it correct or not. Okay. So now let's see the Fourier expansion now. That why are we even studying this? Okay, calm down. I'm telling. Let me raise this. Now assume let fx be a periodic function of period 2L, right? What do I mean by the period 2L? It means that if fx is the function, then f of x plus 2L will be equal to fx, right? For all x, okay? Defined as, defined on x belong to negative L to L, right? Okay. Assume it can be written as a linear combination. It is linear combination of trig functions cos mx and sin nx, suppose. So basically we are assuming a function that is periodic and has the period of 2L, which is defined on x belonging to negative L to L, and we are assuming that that function can be written as a linear combination of cosine of mx and sine of nx, okay? So it means that we have to write fx like this: some constant which we name as a naught by 2 in this case, don't worry, I'm telling, plus since we are doing the linear combination, it means that it will go like this: n pi x by L, okay? You remember the definition of linear combination, I hope so. It is that only, okay? And n is equal to 1 to infinity bn sine n pi x by L, right? So this is a constant, and an and bn are also constant. These are the trig functions, trig sine and cosine, right? And this is your summation, you know it, okay? And this is the function which is given. Okay, so we have written it like this. We assume that it can be written like this, but is it correct or not? We have to check first of all. How? Because so we have written fx like this, but how can we prove it? Well, this is our assumption first of all. So we have to make some adjustments using the constants to make this statement true. So it is only a fixed set of constants which will satisfy this value, and we are going to find that. Okay. So let's see. So let's solve for a naught first of all, right? Okay. So to solve for a naught, let's integrate both sides. Yeah, let's integrate. From minus L to L of fx dx is equal to negative L to L of a naught by 2 dx, right? Plus summation n is equal to 1 to infinity, since an is a constant. We have this quantity negative L to L of cos of n pi x by L dx, right? I hope so it is understandable. Negative L to L of sine of n pi x by L dx. Now notice one thing, that we had proved that this integral and this integral are zero, right? If you remember that when we were checking the orthogonality with respect to 1 and the cos and sine functions, remember that? Okay, which means that this is equal to 0 and this is even 0. Since this is equal to 0, 0 into anything is 0, and summation is still again 0. So this whole expression is 0, okay? So if you evaluate this integral, you will get a naught times 2L by 2 is equal to integral negative L to L fx dx, right? Correct? Okay. So you get a naught is equal to 1 upon L integral negative L to L fx dx. So this is the value of a naught which will satisfy this expression. Okay, so we founded the value of a naught, but still we have to find the value of a n and b n, right? And now for calculating the value of a n and b n, I will change the indices to k, that we have to find the value of a k in this summation, right? I hope you are not understanding right now. I will tell in few seconds. Let me erase this. So now let's solve for a n. So let's assume that we are solving for a value ak, right? Suppose a n is actually consisting of, since it is going from n is equal to 1 to infinity, so it is from a1 a2 till suppose ak, then again. Okay, so ak here, k is an arbitrary number. Okay, right? So now let's solve. Okay, so fx is equal to a naught by 2 plus the summation n goes from 1 to infinity. You can write it like this: a1 cos pi x by l plus a2 cos 2 pi x by l, and so on till ak into cos k pi x by l, right? And so on till infinity, plus this expression, this n is equal to 1 to infinity of the quantity b n sine n pi x by l, right? Okay, now what I'm going to do is that I will multiply both sides by cos k pi x by l. Don't worry why I'm doing it, but just believe me and let me do it, and then I will explain. Okay, so fx into cos of k pi x by l is equal to a naught by 2 cos k x pi by l, summation n is equal to 1 to infinity a1 cos pi x by l into cos k pi x by l, and I'm not writing the second term, you know it. Okay, plus so on till ak cos k pi x by l into cos k pi x by l, and so on, plus n is equal to 1 to infinity of bn into sine of n pi x by l into cos k x pi by l, right? Fine, is it correct? Okay, so notice that now let's integrate both sides, negative L to L, right? Now I'm integrating the same step. Integral negative L to L of the quantity dx. Again, the integral over here, negative L to L, here dx, plus over here also integral negative L to L of the quantity over here, it will be dx, and so on, right? I hope that it is clear. Okay, and similarly integral over here, so negative L to L dx. Okay, now if you remember, this quantity again is 0, right? From the orthogonality, we have proved that this expression will be 0, 1 and cos, right? And this expression is also 0, and the remaining also are 0, except this, it will be ak into l. Why? Because we have proved that cos m pi x by l into cos n pi x by l, integral from negative L to L dx is equal to L when n is equal to m. Over here they both are equal, they both are k, which means that their integral will be equal to L, so ak into L. And notice that sine into cos for any value of n or m, it is always 0. You remember? If you don't remember, you have to go back to the orthogonality and you have to check again that am I saying correct or wrong. Okay, if I'm wrong, then please tell me, and if I'm correct, then also. So if you don't remember, you can check it. So we have negative L to L of the quantity fx dx is equal to ak times L, which means that ak is equal to 1 upon L integral negative L to L fx into cos n pi, I mean it will be k pi x by L dx. Now if you want, you can change the indices or the index from k to n so that it is valid for all expressions, right? Okay, this is n, sorry. I did not use n over here for this term, because if I would have used n, then you would have got confused with this, because it is the summation term actually n over here, and k is a particular index over here. So that is why we calculated for a particular index, then we generalized it using n. Okay, so now it is valid for all indices. I hope so it is clear. So now let me erase this, and similarly if you solve for bn, what you have to do? Okay, You have to multiply both sides by sine k pi x by L and apply the same property over here. Sorry. So apply the same property over here that you again open this. Notice that cos into sine will again become 0, right? And a naught by 2 into sine 1 and sine are orthogonal. So in that case also the integral becomes 0. And here we will have negative L to L of fx sine of k pi x by L, right? Correct. And over here also everything will become 0 except this quantity sine k pi x by L into sine k x pi by L. Rest all becomes 0, just like over here. If you remember, you are multiplying over here. You are multiplying over here k sine into sine of k pi x by L. I hope so it is clear, right? Just like we did over here, the similar is the method over here also, right? You can try it. If you don't get the answer, you can comment me in the comment section and I will guide you there. Okay, so I hope so it is clear now. So let me write all the results over here properly. Let me erase this also. So if you solve for b, and you will get 1 by L into integral negative L to L fx sine n pi x by L dx, right? I told you the method, multiply by sine kx by L and then integrate it, just like you did for cos. You multiplied by cos term, here you will multiply by sine, just integrate, you will get the answer. It is very simple. So this expression is valid for these values of the constants, right? So it is not valid for any value of a naught, a and b n. It is valid for these specific values, right? Okay. So let me see if anything else is left. Well, these are sometimes referred to as Euler's formula for Fourier series, right? To find Fourier series, right? Okay. So now let's see an example to understand this concept better. And yeah, let me raise this. So this is the question, and in this we are asked to write the Fourier series of fx. Okay. And we are given this, that the period is 2 pi, which means that L is equal to pi, right? Okay. Solution. So how we will do it? Well, we know fx is equal to a naught by 2 plus summation n is equal to 1 to infinity a n cos n pi x by L plus summation n is equal to 1 to infinity b n sine n pi x by L, right? This is correct? Okay. Now a naught is equal to negative L to L of the quantity fx dx. So it is negative pi to pi of fx dx. So now you have to break the limit, since the function is broken actually. So we have negative pi to 0 fx dx plus negative pi to 0, I mean 0 to pi fx dx. Notice that fx over here is 0, so this whole expression is 0. So we are left with this negative pi to 0 of fx dx, and it will be equal to, it is pi plus x. So you substitute pi plus x over here. Your negative pi to 0 of x plus pi, or pi plus x dx, you get pi x plus x square by 2. You substitute 0, it will be 0. You substitute negative pi, it will be negative pi square. It will be negative of negative pi square plus pi square by 2. So you will add, you will get pi square by 2. This is equal to pi square by 2, right? Okay. And an is equal to negative L to L fx cos n pi x by L dx. This is equal to negative pi to pi of the quantity fx cos n pi x by L dx. It is equal to negative pi to 0 of the quantity fx cos n pi x by L dx. And I won't write from 0 to pi, because I know that fx is 0 over here, right? Since fx is 0, so this whole expression becomes 0. So I just need to evaluate this. Okay. Okay. negative pi to 0 pi plus x into cos n pi x by L dx. When you evaluate this, you will get, let me see, 1 upon n square pi into the quantity 1 minus negative 1 to the power n, right? Okay. Well, I've applied the integration by parts over here. Of course, we have to, since you can evaluate pi into cos pi x by L, right? And then you will get x into cos pi x by L, and that is simply the integration by parts. I hope so you know it. That is why I skipped the integral part. And now one question is that why it is negative 1 to the power n. So I need to tell that. So when you will evaluate this, you will get something like cos of n pi, right? And one thing I need to tell, it will be pi over here. So it will be also and pi gets cancelled. So it will be equal to nx, right, over here. Now let me tell one thing, that when you will evaluate this, you will get something like this, cos of n pi, right? So when n is equal to 1, let me write it like this. This negative 1 when n belongs to odd, and 1 when n belongs to even, right? Okay. So it means that I can write cos n pi as equal to negative 1 to the power n. Is it correct? When n belongs to odd, it will be negative 1, and when n belongs to even, then it will be negative 1 to the power 2k, which will equal to 1, which means that this is how we are getting here negative 1 to the power n. So if you don't understand that why it is over here, that is the reason that we were getting a cos n pi after evaluation of the limit of the integral. Okay. Sorry. And similarly, we can apply the concept over here also to solve for Bn, that Bn will be equal to negative L to L of fx sine of n pi x by L dx. You substitute the values, and when you solve, you will get over here as negative 1 upon n, right? Okay. So if you will solve, you get negative 1 upon n. Okay. So now let's write this expression in terms of its Fourier series. Let's see. So fx is equal to, what was a naught? A naught was pi by 2. So we will get pi by 2. It was pi square by 2. 1 minute. I just did a mistake over there, that it was a naught is equal to 1 upon L into negative L by L to L, right? So it was fx dx. So I forgot to multiply by 1 by pi over there, so it will be pi square, it will be pi by 2, right? So just remember that you have to multiply by 1 by L also, right? That is why it will be pi by 2. And similar was the case over there also. It will be a 1 upon L into the integral 1 upon L fx cos, then that, and Bn is also 1 upon L negative L to L fx sine, and then that. Okay. So remember to multiply by 1 by L and 1 by L. Sorry, I made a mistake over there, right? So just remember that in all expressions there is 1 upon L. Okay. So it is clear now. So it will be this. Okay, like this. So when you are making the calculation, just see that you have written 1 upon L or not. Okay. I'm really sorry, I made over there a mistake. Actually, 3 mistakes, I guess, because I think in A and B also I did not wrote that 1 upon L. So kindly note that I will write it also at that point when it comes. Okay. So okay. So now let me write this expression. Okay, let me raise this. Plus summation n goes from 1 to infinity of the quantity, what was n when we calculated n, it was equal to 1 upon n square into pi of 1 minus negative 1 to the power n into cos of n pi x by L, plus the summation n is equal to 1 to infinity. What was Bn? Bn was equal to negative 1 upon n. So negative 1 upon n to sine of n pi x by L, right? And if you want, you can simplify it further by opening this summation and then writing 1, 2, and 3 like all the terms, and here also. So you will end up getting a series. Okay. but in summation form it will be like this. Okay, so you can try this problem also. I won't discuss it, but you can try it. Fx is equal to x minus x square. X belongs to negative, or let's say the period is x plus 2 pi to fx. So in this we have to write the Fourier series for this expression, and it is simply we have to use just the formula, right? So apply the formula and you will get the answer. So the method is simply this only, nothing else. In fact, it is simple because here the function is not broken. So I hope so that it is clear. Now let's come to the convergence of a Fourier series. Let's see. So now we are going to see convergence of Fourier series for continuous function. So let's see. Well, I'm really sorry for this condition of paper because some glue had fallen on it. That is why it is in this condition. Kindly ignore this. Okay. So yeah, if a periodic function, if a periodic function of period 2L, I hope so you know the full form, it is period of 2L is continuous in negative L to L, and has continuous first and second derivative at each point in that interval, then the Fourier series, you know how to write Fourier series right now. Okay, Fourier series of fx is convergent. Okay, okay. So basically, if a periodic function of period 2L is continuous, I mean it is continuous, it is not breaking at any point. In the interval negative L to L, of course, there is the value of the domain, and has continuous first and second derivative at each point in that interval. Okay, so it means that f dash x and f double dash x has to be continuous at each point in this given interval, then the Fourier series of fx is said to be convergent. Well, if you want, I can give the proof also. Well, let's see proof also, but if you think it is not of your use, then you can skip that. But I would recommend to see the proof because it is really interesting to understand mathematics using proof, because then it will be just rote learning if you are just learning the statements, right, and solving the problems. It is better to understand it proof wise. But still, if you don't want, you can skip. Okay, let me erase this and then we'll come to the proof. So let's see the proof. We know a naught is equal to 1 upon L. Yeah, 1 upon L negative L to L fx dx. Now I will emphasis on 1 upon L again and again so that there's no mistake in your calculations too, because I also did that mistake. And an 1 upon L negative L to L fx cos n pi x by L dx, and Bn is equal to 1 upon L negative L to L fx sine n pi x by L dx, right? Okay, so I've written the constants value. So what's next? Let's, so an is equal to 1 upon L negative L to L fx cos n pi x by L dx. Okay, so now let's apply integration by parts. Okay, let's do it. So let's assume this as our first function, this as our second function, right? 1 upon L, okay, f dash x, and what is the integral of this quantity? It will be sine n pi x by L upon n pi by L, right? Limits goes from negative L to L. Notice that if you substitute L over here, it will be sine of n pi, which is equal to 0. When you substitute negative L, it will be sine of negative of n pi, which again will be 0, right, for any value of n, which is an integer, which means that this expression is 0, okay, minus the quantity negative L to L f dash x sine n pi x by L dx, right? And n pi by L, so we get over here L by n pi, right? Correct? So L and L gets cancelled. So we have an is equal to 1 upon negative n pi integral negative L to L f dash x sine n pi x by L dx, right? Now again set it as your first function, this as your second function. You just apply the formula of integration by parts. You get f double dash x into the quantity cos of n pi x by L upon n pi by L, and of course a negative will be there over here from negative L to L, right? Now one thing to be noticed, that since fx is a periodic function, which means that f of x plus 2l is equal to fx, correct? Is it fine? Okay. So f dash of x plus 2l will be equal to f dash of x, since we have assumed that this function is continuous and periodic, right? And we are assuming now, that is why in the statement was if f dash x and f double dash x are continuous too, which means that since we assume this as continuous and periodic, so this has to be also continuous. Why? Because we assumed it. So which means that if you substitute x as L, as negative L, you get f dash of L is equal to f dash of negative L, right? Correct? So now when you substitute the limit over here, what you will get, sorry, it will be f single dash x. Sorry, since it was simply that term, okay, there, no derivative involved. Sorry, here also no derivative involved. I'm really sorry. Right, I made some minor mistakes over here which you should not make, like me. Okay, so yeah, it's correct. So so is it fine? Okay, so when you substitute over here, you get f dash of L. Well, don't worry about negative sign, we will see it, cos of, and don't worry about this constant 2, cos of n pi minus f dash of negative L cos of negative n pi, which is again n pi, since cos is an even function, f of negative x is equal to fx, right? Okay, so cos of n pi, right? So notice that cos of n pi into f dash L minus f dash negative L, since we assume that fx is continuous and periodic, and we assume that it would imply that over here, that since f dash of x plus L is equal to f dash x, since we assume that f dash x is also continuous, which means that this expression is 0 since they both are equal, right? Which means that this limit is again 0, right? Fine, correct? Okay. Now again we have this expression negative L to L. Now the derivative of the second, I mean the first function, what the integral of the first, again it is cos n pi x by L divided by the quantity n pi by L, negative negative becomes plus, right? Okay, so let me erase this and then we will see further. Okay, so we have this value of an, right? Okay, now we can further simplify it a bit and we get negative L by n square pi square negative L to L of fx cos of n pi x by L, right, dx. Now f double dash x, sorry. Now since we know that fx is continuous and periodic, which means that and we assume that f dash x and f double dash x are continuous too, which means that since f dash x has a maximum value, so it means that f double dash x will also have some maximum value, right? Suppose f double dash x is less than some quantity m, and of course we have to take the mod over here, right? So which means that let's don't yeah, we take the mod. So let's take mod both sides. What we get? An L by n square pi square, it will all become positive now, negative L to L, f dash x cos n pi x by L dx. Bring the mod inside, and you know the property that this is this quantity, right? If you remember this property, right? Okay. So mod of n is equal to L by is less than equal to n square pi square of the quantity into the negative L to L of f dash x into cos. What is the mod of cos? It will be equal to 1. The max value of cos is 1, right? And what is the maximum value of this function? It will be m. So m dx, right? So we have mod an is equal to the quantity m into 2l, so 2ml square by n square pi square, right? I hope so that it is clear. Okay, so now similarly, if you apply for bn also, when you apply for bn, you use the same methods and integration by parts and all. So when you evaluate it, it will be less than equal to again 2ml square by n square pi square, right? The same result which we got over here, right? Okay, so what's use of these two? Well, don't worry, we are going to see. So we have fx is equal to a naught plus summation n is equal to 1 to infinity an cos n pi x by l plus summation n is equal to 1 to infinity of bn cos n pi sin n pi x by l, right? Okay, now just take this expression and a naught plus summation n is equal to 1 to infinity, or just why we need to write again and again. Take both sides magnitude, and it will be less than equal to a naught by 2 plus summation n is equal to 1 to infinity mod an. Why mod an? Because we know that mod of cos is 1. Okay, plus summation n is equal to 1 to infinity 1 mod bn, right? Again, okay, fine, correct. Okay, so mod a naught by 2 plus summation n is equal to 1 to infinity. Since they both are equal, so we can write 2 over here, right? Since mod an and bn were 2ml square by n square pi square, right? Okay, so we are left with mod a naught square plus 4ml square by pi square into the summation n is equal to 1 to infinity of 1 upon n square. What is it? It is equal to pi square by 6, right? Okay, Euler's formula, Euler series, whatever you want to say. This and this gets cancelled, is 2 by 3, so we are left with mod a naught by 2 plus 2ml square by 3, which means that this sum will be less than this expression where m is finite, l is finite, a naught is finite, which means that this expression is converging, right, to some value less than this. It means it is converging. Okay, let me raise this. Now let's see a piecewise continuous function. Well, what is a piecewise continuous function? Well, a function which is continuous in a broken intervals. What do I mean is that? Let me write some points. A function fx is said to be piecewise continuous in negative L to L if first point fx is defined and continuous in continuous uh, for all x belonging to negative L to L except a few except at except at some, let me write it like this, at some finite number of points. Okay, so suppose that in the interval a to b there is a x naught, there are 3 points c, d and e where the function is broken, is discontinuous. So if the function is continuous in a to c union c to d union e to b, if the function is continuous in this interval, then it is said to be a piecewise continuous except the discontinuities at C, D and E, right? Okay, correct. Okay, so I hope so that I have written it well. Of course, if I need to write it, it shouldn't be like this: C to D, and then D to is E is left, D to E, then union E to B, right? Like this. Well, it was just an idea to tell that if there are three discontinuities in this interval at some point C, D and E, so we will have to check that if in these intervals the function is continuous, then function is said to be a piecewise continuous function. Okay, let me erase this for now and move on to the next point. Okay, what is it? Let's see. Second point, at a point x not belonging to negative L by L, sorry, if function is not continuous, then I mean at x naught, if the function is not continuous, then limit as x naught fx and limit as x belongs to x naught, I mean x approaches x naught plus fx exist and are finite. Okay, basically if x naught is a point where the function is not continuous, then there should be the left hand and right hand limit, they should exist and should be finite, right? Okay. Sorry, at the point of interval limit x tends to negative L from this quantity fx and endpoint and limit x tends to fx exist and are finite. Basically at the end point, right? I was thinking that why point everything. Yeah. So at the point of interval, I mean this is the right hand limit of the negative L, and this is the right hand, and this is the left hand limit of the upper limit, and this is the right hand limit of the lower limit, right? Of course, that after that only function is defined, and before that the function is defined, not after that and before that. Okay, that is why. So basically, these are some of the points related to piecewise continuity of a function, and now let's see convergence of a piecewise continuous function. Let's see what is it. So we are going to see convergence of piecewise continuous function, sometimes it is referred to as Dirchlet conditions too, right? Conditions 2, suppose a function fx can be expressed in Fourier series if provided the function should satisfy such properties if it is a piecewise continuous function. The first one, fx is periodic 2L in negative L to L, right? And is single valued, right? Means it don't take multiple values for a single input valued function, and it's finite, right? Of course it should be finite, as how will, yeah. Second, fx it should be piecewise continuous in negative L to L. Of course it should be. Third, fx has LHD and RHD at each point in interval, right? Okay, in interval, right? Okay, now there is a theorem. It is clear that the function should be periodic, it should be single valued function, and finite, it should be piecewise continuous, and it should have LHD and RHD at each point in the interval, right? Okay, you know what is left hand derivative and right hand derivative, right? Simple it is. Okay, so it is a theorem related to the Dirchlet conditions only. That suppose, I'm not writing a statement or anything like that, you need to just understand. Suppose if function is continuous at x is equal to x naught, then the value of fx naught, then f at x naught, x is equal to x naught, is equal to f at x naught. But if function is discontinuous at x is equal to x naught, then f at x as x is equal to x naught will be given by f at x naught negative, I mean the LHS, I mean not the LHS, it is the LHL value of the left hand limit plus the right hand limit at x naught, right? Okay, else it will be this. Of course this is general, because if they both are continuous, and I mean if the function is continuous at x is equal to x naught, so in that case they both are equal, right? So it means that it will be equal to fx naught, so it is better to write like this only. Okay, so let's see this with the help of an example, right? I hope that this much is clear, right? Okay, let's see with the example. So the question states that we have to find the Fourier series of fx is equal to negative pi from negative pi x and then 0 and x 0 x and pi, right? Okay, so we are given this sorry, and now from this we have to deduce 1 upon 2 square plus 1 upon 3 square and so on is equal to pi square by 8. Well, okay, so of course you can solve for the Fourier series on your own, because you know how to deduce it. You know that you will take the limit as 1 upon L. Yeah, of course you are given over here functions from negative pi to pi, right? Okay, correct. Yeah, one thing I need to tell over here, well I will tell in the later part of the video. Okay, 1 upon L into the quantity negative L to L fx dx, and simply apply for an and bn, and you will get certain result that a naught is equal to negative pi by 2, and an is equal to 1 upon n square pi negative 1 negative 1 over here, and bn is equal to Bn is equal to 1 upon n into 1 minus 2 into negative 1 to the power n, right? Correct? Sorry, correct. So we have fx is equal to a naught by 2, so negative pi by 2 into 1 by 2, so we have negative pi by 4 plus summation n goes from 1 to infinity of the quantity 1 upon n square pi negative 1 to the power n minus 1 plus the quantity n is equal to 1 to infinity of the quantity 1 upon n into 1 minus 2 into negative 1 to the power 2 into the sine function into the this over here cos function. So this is how you will get the Fourier series. And since we need to find this expression, which means we need the square term. So notice that this don't have any square term, so we have to remove this term over here. So how will it be removed? When x is equal to 0. Why? Because sine of 0 is equal to 0, right? Okay. If you needed to eliminate cos, then you would substitute pi by 2, right? Or negative pi by 2. But over here, you will substitute pi, 0 over here, right? So we have f at 0 is equal to negative pi by 4 of the quantity n is equal to 1 to infinity. This will be 0 because sine of 0 is equal to 0. So whole expression will become 0, right? Correct. So n is equal to 1 to infinity of the quantity negative, not negative, n square pi negative 1 to the power this into cos of n pi x by l. L is equal to pi. So pi and pi gets cancelled. You are left with nx, right? Nx, right? Okay. And since x is equal to 0, you get over here 0 and cos of 0 is equal to 1, right? So we are left with this expression. Okay. Sorry, negative pi by 4 plus 1 upon pi into the quantity. Let's open this now. You get when you substitute 1, you get negative 2 by 1 square, negative 2 by 1 square plus 0. Since when n is equal to 2, it will become 1 minus 1, which is 0. When you substitute n is equal to 3, you get negative 2 by 3 square and so on till infinity. What is f at 0? Well, f at 0, over here it is 0 and over here it is equal to negative pi, which means that the LHL and RHL value are not equal. So we have to write f at 0 as f at 0 negative plus f at 0 positive, which is equal to negative pi by 2, right? Correct? Okay. So we are left with negative pi by 2 is equal to negative pi by 4 plus 1 upon pi. 1 upon pi, negative 2 is taken as common into the required sum. This is the required sum. And if you solve it will become negative pi by 4 and you bring it, it will be pi square by 8, right? Hence proof. So Fourier series is also used to find the series. I mean, such kind of series. It is very easy to prove it using Fourier series, right? So this is one of the biggest application also of the Fourier series. And now let's see what's next. Now let's see even and odd functions. What are these? Okay, let's see. So even and odd functions. Odd and even functions. I think you might know about it, or if you don't know, let me tell. If you have a function fx, then if f of negative x is equal to f of x for all value of x belonging to the domain, and f of negative x is equal to f of negative x for all value of x belonging to the domain, then in this case we call this kind of function as odd function and we call such kind of function as an even function. So in the case of an even function, negative L to L fx, let me write it over there only so there is no confusion. So negative L to L fx dx, it becomes negative 2 times 0 to L fx dx, and over here if you have negative L to L fx dx, it becomes equal to 0, right? So this is the application of ordinary function in terms of integrals. So we will use this idea to solve for Fourier series in the cases of even or odd function. So suppose if fx is an even function, right, is an even function, then a naught will be negative L to L fx dx. It will be 2 times 0 to L fx dx, correct? An will be negative L to L of fx cos n pi x by L dx. Now notice one thing, that even into even is an even function, even into odd is an odd function, and odd into odd is an even function, right? Why? Because if you substitute the negative x, so in this case it is negative into negative, which will become positive, which means that it will become an even. Here also it will become positive into positive and even. Here positive negative, it will become odd function, right? So notice that here this is also even, this is also even, so it means that this whole is an even function. So it is this quantity, right? Fx into cos n pi x dx. Okay, bn is negative L to L fx sin n pi x by L dx. Notice fx is an even function, sin is an odd function, right? So it means that their product will be odd function, and odd function integral from negative L to L is equal to 0, right? So remember, when you have an even function, sorry, so when you have an even function, then in that case you only need to evaluate a naught and an, because you will know that bn is already 0, right? So you don't need to evaluate for this function, for this bn, right, in the case of an even function. And in the case of odd function, a naught is equal to negative L to L fx dx. Since fx is odd, odd fx, since fx is odd, it means that this will become 0. And again, an is equal to negative L to L fx into cos of something to dx. So this is odd, this is even, odd into even is odd. So it means this limit, so it becomes 0. bn is equal to negative L to L. Of course, 1 by L, sorry, 1 by L, 1 by L, 1 by L. So it will be 1, it will be 2 by L, 2 by L, 2 by L, right? 2 by L, right? I'm really sorry, I am making so a small mistake over here. So 1 upon L, right, over here also, and 1 upon L over here also, right? Fx sine of the angle dx. Notice that this is odd, this is odd, so odd into odd is even. So it becomes 2 by L of negative of 0 to L fx sine n pi x by L dx, right? Which means that you need to only evaluate bn in case of fx being odd function, right? So there's nothing else which is required to be told in this, because when you solve numerical, you will apply the same concept as you applied over there before. But now if you see odd function, you can directly say that a naught and n is equal to 0. You will only solve for bn, right? It will save steps. Else if you apply the original method also, it is same, right? So if you want, if you see an odd function, you can directly say a naught and an is equal to 0. So you will only solve for bn. And if you see an even function, you will solve for a naught and bn, and you will say bn is equal to 0. And if you don't want to remember odd and even function anything, you just solve for a naught, an, and bn, right? Just like you were doing before. Okay. So now let's see what is Fourier half range series. Let's see what is it. So suppose Fourier series expansion of a function fx in an interval, in an interval 0 to L, where L is half of the period, right? Period, because the period is 2L, so L is 2L by 2, that is half of that period, right? Then it's possible, it's possible to extend fx, function fx, in other half, negative L to 0 of negative L to L, like this you can also write, so that function is either odd or even. Wait, Now, before saying anything after it, let me explain what is it, right? Because I know it is going like a bounce. So let me explain it. Okay. So suppose this is the function, right? Suppose this is like this, okay? 0 to L, right? You can assume it like this. Suppose this is a very simple example, which generally given in every textbook. If you see or if you follow any teacher, it will be any professor, it will be the most basic example that anyone will give. Okay, so suppose this is the function from 0 to L which you are given, so you can extend it back like this also. It should be symmetric actually. Let Yeah, so this was original. Now you extended, this is extended even function. How? You check for any value of x, they both are equal. It means f at negative x is equal to fx, and since it is symmetric about the x axis, sorry, about the y axis, right? So it means that it is an it is an even function, right? So it is an extended even function, and in this case this is extended odd function 0 to negative L, right? Since it is reflected about the origin, right? Okay. So what is the use of this? Well, let me explain it. If I say in general, you won't find much use, right? But when you solve problems, it might be used somewhere or somewhere not. It will be explained in the question properly. But in general sense, it don't have much application like that as an individual, right? But let me explain it through a question also. But before that, let me see that if I need to tell anything. Yeah. Suppose if we are extending it as an even function, so if you write the Fourier series, it will be a naught is equal to 0. Sorry, a naught is equal to 2 by L negative L to I mean 0 to L fx dx, and a n is equal to 2 by L 0 to L fx cos of n pi x by L dx, and you will set bn is equal to 0, right? So when you are asked that to write the extended Fourier series for even function, it will be this. I mean the constants will be this, right? And when you are asked for this, a naught is equal to an is equal to 0 and bn is equal to 2 by L 0 to L fx sine n pi x by L dx. Just like in the case of even and odd function, there's nothing new in it. Okay, so that is why I said that if you know even and odd function, you can do it very easy. So if I give you a problem, it is similar to the problems you just did before, or you can apply even or odd function also, right? That is the key. Let's see with respect to a question also. Okay. Okay, before coming to an example, let me tell you one thing. Suppose fx is given like x, and for negative pi to 0, and suppose it is 0 for like this. Okay, fine. So if you are asked to write the Fourier series of it, you know how to write it. But what exactly does this statement tell? Fx plus 2 pi is equal to fx. Let me explain it graphically. Suppose this is your x-axis, this is your origin, so this is origin, and when x is negative pi, then y is also negative pi. I mean it will be somewhere over here, right? Okay. So it goes like this, okay, and then from 0 to pi it is constant, right? Till here this is negative pi and this is pi. So what will happen is that this graph will keep on repeating itself, right? This is meant by a periodic function. I hope so. Now you understood that what I was saying, right? That this graph will keep on oscillating like this. This is 3 pi and so on and so forth. This negative 3 pi, right? Like this. Sorry, not over here. Over here. Okay, like this actually. So now I hope that you understood what is meant by fx plus 2 pi is equal to fx for a given function, right? Simple, right? Let me erase this and now we will see a problem. So question, obtain cosine and sine series for fx, Fourier series basically, Fourier series fx is equal to x in 0 to pi, I mean 0 to pi, right? So what do I mean by cosine function? Well, it is just even function, right? So we have to express it in terms of even and odd function, right? First even and then first odd. I mean first even then odd, okay? Fourier series. So it means that we first need to solve with respect to the even extension, then odd extension. This is how it will be asked, okay? So a naught will be equal to the integral 2 by pi 0 to pi x dx, right? Correct. So it is pi square by 2, pi square by 2. So it turns out to be pi, right? Correct. Am I correct? Yeah. So an is equal to 2 upon pi integral 0 to pi, and then this x cos n pi x by l dx. I won't solve this. What we will get? We will get 2 by pi 1 by n square negative 1 n minus 1. This. So you get fx as pi by 2 minus 2 by my 2 by pi. Let me see if I made any mistake or something like that. No, plus, sorry, of the quantity summation n is equal to 1 to infinity of 1 by n square negative 1 to the power n minus 1 into cos of, since x is since l is equal to pi, so we have cos of nx, right? Like this. Okay, so this is the even Fourier series for this even or the even extension. Okay, this is a Fourier series for the even function or the cosine function. And similarly for the odd function, bn is equal to integral 0 to pi 2 by pi of the quantity x yx, because fx is equal to x, right? Okay, of sine n pi x by l, and it is equal to, what is it equal to? I have to see, it is equal to 2 into 1 negative 1 to the power n plus 1 by n simply. So you get it as fx summation n is equal to 1 to infinity of the quantity 2 is common, so you get negative 1 to the power n plus 1 by n into sine of nx, right? Simple, right? So this is the odd extension. Fourier series for the odd extension, right? So I have that. Now you understood that what is meant by half angle, right? Not half angle, it is the half range, sorry. Half angle I was saying for trigonometry, sorry. So this is for a half range. Okay, so now let's see what is Parseval's identity, and then we will see the complex form of the Fourier series, and then we will end the lecture, right? I hope that till now everything is clear. If it is clear, then please do like, subscribe my channel, and please support this video. Okay, so now let's start with the Parseval's identity, right? So let's see Parseval's identity. What is it? Well, it basically states negative L to L of the quantity fx whole square dx is equal to L times 1 by 2 a naught square plus summation n is equal to 1 to infinity a n square plus b n square, right? This is the Parseval's identity. Well, of course, now you might be thinking that how it has come, so I'm going to give the proof. Okay, let's see the proof. Okay, So fx is equal to a naught by 2 plus summation n is equal to 1 to infinity of an cos n pi x by l plus summation n is equal to 1 to infinity bn sin n pi x by l, right? You are given this, and now what you are going to do is you will multiply both sides by fx, right? A naught by 2 into fx plus summation n is equal to 1 to infinity an into fx cos this n is equal to 1 to infinity bn times b times fx sin n pi x by l, right? Okay, now what I'm going to do is I will integrate it dx, okay, minus l to l dx minus l to l dx minus l to l dx. Now notice that well, a naught by 2 is a constant, so I can bring it out. So notice that let me write it over here. A naught was equal to 1 upon L negative L to L fx dx. Same thing is written over here. Let me write it like this, then it will be more clear. A naught by 2 integral negative L to L, right? Same thing is over here, just we have to bring L over here. So it is L A naught. So negative L to L of fx whole square dx is equal to L times A naught into A naught by 2. It is L A naught square by 2 plus. Notice that an was equal to 1 upon L negative L to L of fx cos of n pi x by L dx. Bring it over here. So it is equal to L times an, right? Correct. So it is n is equal to 1 to infinity of L times an into an whole square. Similarly, you can solve over here also. It is same. It will be equal to 1 to infinity L b n whole square, right? Correct. You now bring L outside, you get negative L to L fx whole square dx is equal to L times a naught by 2 plus this quantity an square plus bn square, right? Okay. So hence you got this identity, right? And if functions even or odd, it don't matter, this is a general expression. You can make some adjustments to solve, else you don't need it also, right? You just apply this formula and solve. Okay, so there's no adjustment actually, you just need to just apply the properties, nothing else. So I'm not going to that. If you want, you can prove it on your own also, else you don't need, just you need to remember this formula if you want. Okay, let's see an example. Yeah, and there's one more thing, RMS value of a function in a to b, right? Okay, so f rms is equal to integral a to b fx whole square dx upon b minus a, right? This is how you evaluate the RMS value, and of course you must have studied it in physics and some other subject, but since it involves fx whole square integral, so that is why I told it. Okay, okay, so now let's see an example. Okay, let me erase this. Okay, question: apply Parseval's theorem, I'm not writing the full form, to the function fx is equal to x negative pi to this and this. Okay, and this. Okay, f of x plus 2 pi is equal to fx, right? Okay, now notice that when you solve for a naught, what you get? A naught is equal to integral negative L to negative pi to pi of fx x dx, it will be equal to 0, right? Correct. And an is equal to negative pi to pi and x cos n pi x by L dx, it will be also equal to 0. Why I am saying like this? Because x is an odd function. That is why, don't worry that how am I calculating like this. And bn is equal to negative pi to pi. Now this we have to calculate. x sine n pi x by l dx. It is equal to what? Let me see. It is equal to 2 times, well, we have calculated this actually, I think, and right, n plus 1. Okay, so this is what we need to do. What we need to do in this is that we have to prove to deduce sum 1 upon n square is equal to pi square by 6. Okay, this is the Euler series, if you remember. Okay. So fx, so now we are going to apply the Parseval's identity. Now we know that negative L to L of fx dx whole square is equal to L times the summation n goes from 1 to infinity of b n square, right? So over here substitute L as pi, fx at x, this is pi, b n, you know the value. Integral of x square is x cube by 3, and you integrate it from negative pi to pi, you get 2 pi by 2 pi cube by 3 pi times this summation n is equal to 1 to infinity of the quantity 2 negative 1 to the power n plus 1 by n whole square, and you solve it. What you will get is that uh, what you will get is that is it pi times, yeah, 2 pi square by 3 is equal to 4 times, since square of a negative number is now positive always, n equal to 1 to infinity of 1 by n square, you bring it over here, so it will become pi square by 6. Correct? So this is how you deduce this, okay, using the Parseval's identity. If you would have used the cos formula and all in that, you would have to use lots of adjustments. In this it is clear, right? So I hope that you understood what is Parseval's theorem. And now we are coming to the last part of this lecture, that is the complex form of the Fourier series, right? Let's see it. Now let's see the complex form of Fourier series, and it is used to make our problems simple. The name suggests it is complex, but actually it is used to make our problems simple. So let's see it. Okay, so the original series looks like this. An sine cos n pi x by l plus summation n is equal to 1 to infinity bn sine n pi x by l, right? Okay, now if you need to convert it to complex form, you know e to the power I theta is cos theta plus I sine theta, right? E to the power negative I theta is equal to cos theta minus I sine theta, correct? Simple. Add and solve, you will get cos theta e to the power I theta plus e to the power I theta by 2. Sine theta is e to the power I theta minus e to the power negative I theta by 2i, right? Okay. Now just substitute it over here, the cos and the sine values. What you're going to get is that fx a naught by 2 plus summation n is equal to 1 to infinity. Well, you can take summation as common since they both have the same indices, right? Okay. So an times e to the power I theta plus e to the power negative I theta by 2 plus bn e to the power I theta minus e to the negative I theta by 2i. Here theta is equal to n pi x by l. Okay, so don't worry. Okay, I'm just going to substitute it back in 1 or 2 steps, but for now I was just doing like this. Notice that you have e to the pi theta over here and over here also, and negative over here. So let's club them together. So you have fx is equal to a naught by 2 plus summation n is equal to 1 to infinity of the quantity an plus bn, right? This by 2i, this by 2, e to the power I into n pi x by l, right? Plus an by 2 minus bn by 2i of the quantity e to the power negative I n pi x by L. I hope that it is clear how I made this step, right? Okay. So let's write one more step over here. So a naught by 2 plus summation n goes from 1 to infinity of the quantity an plus this becomes minus I times I, it will become negative ibn by quantity 2I into e to the power I n pi x by L plus an plus ibn by 2I e to the power negative I n pi x L by n pi x by L, right, like this. Now let me erase this and then we are going to solve further. Okay. Yeah, and notice one thing, that there was no I over here because I take the conjugate and I brought that I to the numerator, so there is no I in the denominator. Okay. Now let's name a naught by 2 as c naught and a n minus ibn as by 2 as cn and an minus an plus ibn by 2 as c minus n. For now just name it as negative n. I will tell why we are naming it like this in just few steps, right? So basically it is equal to c naught plus summation n is equal to 1 to infinity, and notice one thing, that c of negative n is equal to the conjugate of this, right? Since I, if fx is real, right? Okay, if function is real, okay, n is equal to this cn e to the power I n pi x by L plus c negative n e to the power negative I n pi x by L, right? Okay. So now notice one thing, that if you bring the summation inside, you get c naught plus sum as n goes from 1 to infinity c n e to the power I n pi x by L plus summation n goes from 1 to infinity c of negative n e to the power negative I n pi x by L, right? Now notice one thing, if you substitute negative 1 as t, or you replace negative n with n, what you will get over here in this expression? Let's see. Negative to c negative n e to the power negative I n pi x by L. You replace negative n with n, you get n goes from negative infinity to negative 1 of c n e to the power I n e to the power I n pi x by L, right? Which means that this term is from from n is equal to 1 to infinity, and this one n is equal to negative infinity to negative 1. So it covers all the terms from negative infinity to negative 1, and it covers all the terms from 1 to infinity, and this covers at n is equal to 0, which means if you combine all these three, you will end up getting fx as equal to the summation n goes from negative infinity to infinity of cn e to the power I n pi x by L, and this is the complex form, right? I'm sorry. And okay, I hope that you understood this. Now the question is that what is cn? Let's see what is it. Okay, let me raise this, then we will see further. Okay. Okay. Now notice that cn is equal to an minus ibn by 2, correct? Okay, how do you evaluate an? As 1 upon L into the integral negative L to L of fx cos n pi x by L, correct, minus I times fx I by L, right? Okay, fx sine n pi x by L dx, correct. Now you can take fx common, and what you will get is, of course L is a constant, so this will come like this, and minus L to L fx times cos n pi x by L minus I sine n pi x by L dx, right? You got this? Okay. Now this will be equal to e to the power negative, so it will be equal to e to the power negative I n pi x by l. Am I correct or not? Am I right? It is actually. We evaluated it earlier. 2l integral negative l to l fx, right? Fx e to the power negative I n pi x by l is equal to Cn, right? Correct. Okay. So this is the value of Cn, and notice if you substitute, wait, let's solve for C for negative, C of negative, and also it is equal to a, and I mean it will, when you will solve it, it will come like this: 1 upon 2l times integral negative l to l fx e to the power I n pi x by l dx C of negative n. Just apply the same property over here. Instead of negative sign over here, you will get a positive sign, so it will become e to the power plus I n pi x by l, right? So notice that you can create C of negative n using C of n if you replace n with negative n, right? Correct. And if you replace n as 0, you get C naught, which means that this is a general expression where Cn is equal to 1 upon 2l integral negative l to l fx e to the power negative I n pi x by l dx, right? Correct. Okay. So now let's see a question on it, and then we will end this lecture. Okay. So fx is equal to e to the power negative x, and x belongs to negative pi to pi, right? Okay. So let's solve for, first of all, Cn. Cn is equal to 1 upon 2 pi, here L is equal to pi, negative pi to pi, e to the power negative x into e to the power negative I n x n n pi x by pi dx. And if you evaluate this integral, it will be, wait, negative pi to pi into pi, and pi gets cancelled, right? So let's solve for En. What you will get is that, let me write directly the answer. So you get the value of Cn as e to the power pi minus e to the power negative pi by 2 pi into negative 1 to the power n to negative 1 minus in by 1 plus n square. And it is really simple, since it is very simple actually. If you evaluate, you will understand, right? It is simply equal to like that. Okay, you substitute the limit, and when you will solve for the limits and all, remember e to the power I n pi you will get somewhere. So e to the power I n pi is equal to sine of n pi plus e to the power sine nx n pi. Sine of n pi is equal to 0, and cos of n pi is equal to negative 1 to the power n, right? Okay, so you have to remember these things. That is why you got a negative 1 to the power n. Okay? So that is the thing which you need to remember while making calculations. And now let's see fx is equal to summation n is equal to negative infinity to infinity of the quantity negative 1 minus I n 1 plus n square negative 1 to the power n e to the power pi minus e to the power negative pi by 2 pi into e to the power I n x, right? So this is your Fourier series in terms of complex form, in complex form basically. So I hope that you enjoyed this lecture, and if you did, then please do like, subscribe my channel, and I hope so that I've covered everything in this lecture. And if there's anything left, please tell me in the comment section. I will try to add in it or make a separate video on it. And please do like, subscribe my channel, and please support this video, and please support my channel. And now let's end the video, but it really takes lots of effort to make this kind of video, so please do support this video and channel. Please support my channel, and please subscribe my channel. Bye bye, take care.